So the final talk is about homomorphic secret sharing with verifiable evaluation by Arkari Chaudhary, Arushi Goyal, Aditya Hegde, and Abhishek Jain. And Aditya is giving the talk.
Thanks for the introduction, Mingyuan. So this is homomorphic secret sharing with verifiable evaluation. This joint work with Arka, Arushi, and Abhishek. Let's get started. So homomorphic secret sharing is a scheme that allows a client to secret share its inputs to a set of servers so that the servers can locally go from the input share to shares of the output given a function f, which can then be reconstructed. So the correctness property of the scheme guarantees that the output shares computed by the servers are really additive shares of the function output. Security guarantees that given if the adversary corrupts a strict subset of servers, the adversary does not really learn anything about the input. And since the servers compute additive shares, we also have succinctness, where the output shares are of the same size as the function output. And intuitively, homomorphic secret sharing allows private delegation of private computation, which, because of its non-interactive evaluation of the servers and the fact that they compute additive shares of the output, has led to a number of applications in MPC with sublinear communication in the size of the circuit, private information retrieval, and generating correlated randomness. There have been a number of prior works which show how to construct HSS schemes from a wide variety of assumptions. In particular, depending on the assumptions, the HSS schemes support a restricted class of computation. And in general, weaker assumptions give somewhat weaker classes of computation. And importantly for this work, all of the prior schemes, except one exception by Abraham, Damgard, Orlandi, and Scholl, which we'll get to later, are in the semi-honest setting, where the servers are assumed to be honest and that they follow the description of the protocol. In this work, we consider HSS schemes which are in the malicious server setting. And in general, when the servers are malicious, the HSS scheme does not provide any guarantee on the correctness of the output. So what we propose is homomorphic secret sharing with verifiable evaluation, which provides a way for the client to verify the output of the computation. So obviously, if the servers are honest, we want the output to reconstruct to the function output and for the verification to succeed. But what we require now is what we call as local soundness, which is if the client can successfully verify the output, then it is convinced that the output is actually f of x, where x is its input and f is the function it wanted to compute. Why do I call it local soundness? Well, an advantage of homomorphic secret sharing is because the servers compute additive shares of the output, it can be publicly reconstructed. And we want a way for the publicly reconstructed output, an external party, to also be able to verify the output. So to do this, we say the input consists of two parts, a private part and a public part. And the public part is available to everyone, while the private part is only known to the input sharing client. What we want is public soundness, where an external party is convinced that, okay, if verification succeeds, that there is really a private input with respect to which the output is consistent for the public input. So in general, to summarize, we have correctness and two notions of soundness against malicious servers, one for the client that holds the complete input, and one against external parties that might hold a part of the public, that holds part of the input. What about privacy? Well, because the input is secret shared, we can't expect privacy to hold when all servers are corrupt. So we consider privacy in the case where at least one server is honest. And in this case, what we require is that the corrupt server's input share preserves the privacy. And moreover, we can simulate the output share of the honest party, as well as if the client aborts or verifies when it verifies the output. Basically, this means that this corrupt server can't deviate from the protocol and learn something about the input by learning if the client aborted or not. Finally, we require succinctness, which basically says that the size of the input shares and output shares and the runtime of the verification must be sublinear in the size of the function being computed. So we can extend all these definitions to the multi-client setting too. And while we won't be touching much upon this aspect, the details are in the paper. So we understand. So there we have defined a notion called homomorphic secret sharing with verifiable evaluation. But what does this imply? So let's just briefly go over the implications. In particular, local soundness is allowing a client that has the complete input to get the output from the adversary and be convinced that the output is correct. And along with the succinctness property, this really implies a snark for P, right, for polytime computation. Similarly, public soundness plus succinctness implies a snark for NP, where the private part of the input takes on the role of the NP witness. Finally, the notion of privacy that we have for homomorphic secret sharing with verifiable evaluation is similar to the privacy notion in MPC. And again, because the evaluation is non-interactive and communication is, the share sizes are succinct, it's really MPC with sublinear communication in the size of the circuit. And this is the exception that I talked about before. This is the sort of setting, the maliciously secure sublinear MPC is the setting in which prior works have explored maliciously secure HSS. And in this work, we want the stronger notions of soundness when all servers are corrupt, essentially. So let's coming to our results. So what we propose verifiable HSS with verifiable evaluation that make only black box use of cryptography. And our approach is basically a compiler which takes a ZK snarg and an HSS with negligible correctness error and outputs a HSS with verifiable evaluation. In particular, we require a special class of ZK snargs, which we call splittable ZK snargs. We'll get to that later, but for now, you can think about this as some sort of compiler-friendly ZK snarg. So then we instantiate our compiler with the Groth 16 ZK snarg, which is in the generic bilinear group model, and HSS schemes from prior works, to get HSS with verifiable evaluation for NC1 and P over poly, where the class of computation is is a function of the underlying HSS scheme we use. Similarly, we also construct a ZK variant of the batch argument from Waters-Wu. And using this with the prior HSS schemes along with our compiler gives us HSS with verifiable evaluation for SIMD NC1 and SIMD P over poly. Here, the SIMD aspect comes from the fact that we're using a batch argument, and the NC1 and P over poly aspect come from the underlying HSS schemes. So we also give similar results in the multi-client setting using a similar compiler that, again, make only black box use of cryptography. And we showed an obvious application of HSS with verifiable evaluation is that it allows private and verifiable delegation of computation, where verifiability holds even when all servers are corrupt. Interestingly, we also show that we can use HSS with verifiable evaluation, our compiler specifically, to delegate ZK snark computation, which is really a cryptographic computation, while still being black box in crypto. So for the rest of the talk, I'll be mostly going over the compiler and seeing what techniques we use to instantiate it. So the classical approach, the most standard approach to go from semi-honest MPC to maliciously secure MPC is the GMW paradigm, where every party basically proves that it computed the message correctly, honestly. So following this paradigm, what we could do is the client shares the input to the servers. The servers compute the HSS evaluation for some given function f to compute the output shares. And then they prove that they actually computed this HSS evaluation honestly. They then send the proofs, the snags, as well as the shares of the output, which can be reconstructed. And now to verify, we verify that each server actually followed its evaluation algorithm. And we accept or reject if, depending on if both proofs verified or not. While this somewhat seems to work, the main issue is that we are making non-black box use of cryptography, because any non-trivial HSS scheme that supports non-trivial homomorphism requires cryptography, and we are using the prover to show that the evaluation was done correctly, which makes non-black box use of crypto. So our approach is for the parties to compute a single proof jointly to prove the validity of the output. So let's see how we can do this. So naively, again, the client secret shares its input. Then the servers use the evaluation algorithm to first evaluate the underlying function and compute shares of the output. Then they run the zk-SNARK prover within the evaluation algorithm and compute shares of the proof. Now the proof shares as well as the output shares can be reconstructed to compute the proof and output. And here the proof basically proves that the output y is indeed computed as f of x, where x is the input. Now this proof can be verified. There's a single proof which can be verified, and we abort or reject depending on if it verifies or not. But it seems like we've actually taken a step back, because what we've done now is we still seem to be making non-black box use of cryptography, because the proof is run within eval, right? And a zk-SNARK prover would use cryptography, and we are running that within evaluation. And moreover, we seem to have lost privacy now, because what if the corrupt server can send malformed shares of the proof, which then leak something about the input? It's a sort of like a selective abort attack. So to fix this, the main sort of contribution is showing that we can actually realize this approach. And to do this, let's consider a special class of zk-SNARKs, which we call splittable zk-SNARKs. So let's see what the properties are. So a general zk-SNARK prover would take a statement and output a proof. And for a splittable zk-SNARK, what we want it to consist of two parts. The first part is a non-cryptographic computation that takes the statement and witness, outputs some intermediate output. And we want the second part to be an additively homomorphic mapping. What does this give us? Well, now we can, given HSS shares of the statement and witness, we can run the first part within the HSS evaluation algorithm. We'll get shares of the additive shares of the intermediate output, this is what HSS gives us. And because the second part of the prover is an additively homomorphic mapping, we can go to additive shares of the proof. And observe that we are only running the first part of the prover within HSS evaluation, which means that this makes this means that this is really black box in cryptography. But there seem to be some other issues. So most HSS schemes, like we saw before, support a limited class of computation. And this means that the first part of the prover must be, in some sense, simple to compute. And in particular, it must be a low-depth circuit, because a lot of the group-based HSS schemes support NC1 circuits. So we've really placed 3 restrictions on our zk-SNARK prover. We want it to be able to split into 2 phases. We want the first phase to be a non-cryptographic computation, the second phase to be an additively homomorphic mapping, and the first phase should be simple to compute. So do these zk-SNARKs actually exist? Yes, and this is what we show in our work, that Groth16 and the ZK, the zero-knowledge batch argument that we get from what is who really has these properties. So now, given a splittable zk-SNARK, how can we realize our approach? Now, putting everything together, the client secret shares its input. The server first evaluates the function to compute the output shares. Then it runs the first part of the zk-SNARK prover to get the shares of the intermediate output. They then use these intermediate outputs to run the second part of the prover, which is, again, since it's an additively homomorphic mapping, you can get shares of the proof, which can be reconstructed to get the final proofs. This proof proves that y is valid, which can then be verified. So the soundness of the proof pi here basically ensures local soundness of the scheme. But now for public soundness, what we do is we compute another proof. And this proof is for a different statement that shows that there exists a private witness that, so with respect to which the output is consistent. And the soundness of the second proof row gives us public soundness. But we haven't really touched upon the second issue, which is that because the shares could be malformed, the shares of pi and rho here could be malformed, if the client could not verify it successfully, then would it leak anything about the private input? But turns out this is not the case. We show that these proof systems have a property called robust verification, which we call robust verification, which basically ensures that any time the servers deviate from the protocol and send an invalid share, incorrect share, the proof fails to verify with overwhelming probability. This means that the simulator can always just simulate an abort of the client without really knowing the private input. And yeah, that's the end of my talk. Thank you for your time.
Any questions? So maybe I'll ask a quick question. So if I want to extend your scheme to more proof systems, what are the barriers there, and is there any hopeful approaches?
What we really need is a splittable ZK snark, and in general, it seems like any linear PCP-based ZK snark should somewhat be compatible with our compiler. So what do I mean by this? So a general way to one template to construct ZK snarks is to start with a linear PCP and have the verifiers queries embedded in the CRS, and then you basically do an inner product with the PCP. So as long as this linear PCP is somewhat simple to compute, then we can do it within HSS. And then the CRS, the verification queries embedded in the CRS is like an additively homomorphic mapping. So any ZK snark that follows this template is compatible.
I see. Yeah. Thanks. Are there any more questions? If not, let's thank the speaker again and all the speakers in this session. I think.